So the last part of this chapter really covers a variety of different topics to make sure we review them before we begin the calculus part of the course. So let's just talk about a few different types of functions first. So I'm talking about polynomials. Polynomials have the form and it might look complicated, but it's really more straightforward than what it looks like. F of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot dot dot, following this pattern of the n's reducing by 1 all the way to a sub 1 x to the first power plus a sub 0, which would be x to the 0 power after it, but x to the 0 power is just 1. So where all these different a's, right, a sub n minus 1, dot dot dot, all the way to a sub 0 are real numbers. You've probably seen this used as like a, b, and c if you're talking about a quadratic function, but you know, we can't determine how many coefficients we're going to need. Just knowing that these a's are all just different real number coefficients in front of the corresponding x values, and n, right, n being the highest power you see here, is the degree of the polynomial. So when I say the degree, I'm looking at the highest power you see, and the important thing about n is that n is a non-negative integer. In other words, the whole number. So you've probably seen things in this form, you just don't recognize it immediately. Just some quick examples. You know, if I was to say I had f of x equals 3x to the 7th minus 4x to the 5th plus 9x squared minus 1. First off, it's a polynomial because all the powers on these are positive whole number values. The other thing to notice is I don't need every single x represented, right? So when I had these values up here, some of these coefficients could have been 0. In other words, I don't need every term present. I just need to look at what the highest one is. So the degree for this first one, what's the highest power you see? The degree is 7, because the highest power you see is 7. You could have all the terms present, right? If I said g of x equals 4x to the 5th minus 7x to the 4th plus 2x cubed minus 9x squared plus 5x minus 12. Again, it's a polynomial. This one has all the terms present from 5 all the way down in terms of the exponents. But the degree, again, is just based on the highest power you see. In this case, degree will be 5. Let's look at one more special case. If I said I had h of x equals just 15, what's the degree here? Well, the highest power of x that you see? Well, I don't see a power of x here. The degree here is actually 0. Because really, like, it's x to the 0 power is what makes this work, because x to the 0 power is just 1. The only other thing to note for polynomials, just for as we go forward in the course, is the domain for polynomials is always all real numbers. So is negative infinity to infinity. So no matter what polynomial you have, your domain is negative infinity to infinity. In other words, you can substitute any x value in and you will always get a y value out. There are no problem points that could occur here. The next type of function we'll talk about is rational functions. Rational functions are given by the quotient. Quotient means division, right? By the quotient of polynomials. So if you have the part that we just talked about, polynomials, and you have one divided by another, you get a rational function. Just some examples of what they would look like. You know, if I had something like f of x equals 3x squared plus 5 over x squared minus 9x plus 18, that's a rational function. You could have monomial terms, meaning single terms in either the numerator or denominator. You know, g of x equals a 2x over 4x squared plus 3x minus 9 is also in this form. All right, and we've talked about this in other videos, but just to make sure you don't forget, to find the domain of a rational function, you're going to look for the problem points. When I say look for the problem points, though, in this case, we're talking about what could possibly make the denominator 0. So we use the set of numbers that do not cause the denominator to be 0. So what we want is all the values that work in the functions, and we exclude anything that causes the denominator to become 0. And we'll look at an example here. So if I said, in this example, find the domain for h of x equals x plus 5 over x squared minus x minus 2. To find the domain here, what I really want to do is find the values that cause the denominator to become 0 and then exclude them. So I'm going to set x squared minus x minus 2 equal to 0 and then exclude the values that cause this to happen. So to solve this, I'll factor. Here we got x times x. For our first part of FOIL, one thing's to multiply to -2 and add to -1. So that'd be -2 and +1. And if you remember how to solve this, you set each of these equal to 0. So we set x minus 2 equal to 0, x plus 1 equal to 0, setting each of our factors equal to 0. And then solving this, you know, I'll add 2 to each side, I get x equals 2. Here I'm going to subtract 1 and subtract 1, so I get x equals -1. Now these are the values that cause the denominator to become 0. What that means is that we want to exclude these, right? So exclude these. So when I write the domain, it's everything but those points, right? So my domain, we could say, is x doesn't equal 2 and x doesn't equal -1. If I asked you to write this in interval notation, the same thing, except for you're not using -1 and 2. Make sure you know what it looks like. Here's -1, here's 2. We're not using those, but we're using everything here, and everything here, right? Up until those values. So, writing this in interval notation, we would be left with, starting from left to right, we start at -infinity. You need to put a parenthesis there because you don't include it. all the way up to -1, not including -1 because there's an open circle. So parenthesis, union, and then don't forget this part in between. That's the part people miss the most often. From -1 to 2, so parenthesis, -1, up until 2, parenthesis on that because it's also an open circle. And then union, everything to the right of 2 means you start with a parenthesis on 2 and you go out to infinity. And that would be the domain in interval notation. Let's take a look at one more here. If I said, for this example, to graph f of x equals x squared minus 4 over x plus 2. So again, this is a rational function. It has a polynomial numerator over a polynomial denominator. And we're going to try to find the domain, and then I'm going to graph it. So when I look for the domain, remember I want the values that cause the denominator to be equal to 0 to be excluded. So for my domain, you probably don't even have to show work for this. You could show x plus 2 equals 0 and then eliminate what you get. But it might be obvious to you that if you set this equal to 0, -2 would be the problem point. So our domain is x doesn't equal -2. And that's the domain. You could, say x plus 2 equals 0, subtract 2 from each side. So x equals -2. Remember, when we talk about domain, we're only looking at what causes this to become 0 in the denominator. That's why I don't have to manipulate the numerator at all. Now, to graph this, before we do, I want to talk about factoring this function. So if I factor both the numerator and denominator completely, I'm left with this here, right? I would have f of x equals, we have x squared minus 4 over x plus 2. Factoring this, I know that I have x squared minus 4 is the difference of perfect squares. That factors to x plus 2 times x minus 2. You got to remember the factoring rules here. Over down here, x plus 2 doesn't factor, so let's keep it as x plus 2. And then if you remember, you're allowed to cancel these, right? So I can cancel the x plus 2 with the x plus 2 here, provided that this isn't 0. If I'm canceling zeros, then that'd be indeterminate form. But we know that x doesn't equal -2. -2 is what would cause this to be 0, right? So that's not in my domain, so I can cancel those. So it's just equal to x minus 2 for everywhere except for when x doesn't equal -2, right? So all values except for when x equals -2, it behaves as x minus 2 would. So really what we know from this is f of x is equal to x minus 2 except for at x equal to -2, because that point's excluded from the domain. So f of x is the same graph as y equals x minus 2. It's the same graph as this, right? It started out as x squared minus 4 over x plus 2, but it behaves the same as x minus 2. So except for at x equals -2, where there will be a hole. So at that point that we excluded, right, if you cancel out the same factor from both the numerator and denominator, that tells you there's going to be a hole there. That doesn't happen like in our previous example because the factors didn't cancel out, right? When I factored this down here, I would have had an x minus 2 times x plus 1 down here. Those wouldn't have canceled with the x plus 5. Notice this doesn't change our domain at all. Our domain is still x doesn't equal -2 because there's going to be a hole there. But what it does is it tells us if we cancel the same factor out, there's going to be a hole in the graph and it behaves as if you canceled those factors. So what does this look like? Well, let's do a graph here. If I was to graph this, right, what I'm really graphing is y equals x minus 2. So what we know about y equals x minus 2 is that it has a slope which is equal to 1, which you can write as 1 over 1 because we're going to use the graph, and it has a y-intercept of 0, negative 2. Right? So that's our slope-intercept form. We know the pieces we want to graph. So if I was to graph this, right, and it has a hole at x equals negative 2, we're going to graph this kind of like we normally would. So I'm going to graph, I'm writing it up here so it's easier to see, y equals x minus 2, and x doesn't equal negative 2. And we know there's a hole there, just in summary. So first you plot your y-intercept, which would be at 0, negative 2, coming from our formula. And that's okay. The hole only occurs at x equals negative 2. The slope being 1 tells us we're going to move up 1 and over 1 to the right. So from here, I'm going to move up 1, over 1 to the right, up 1, over 1 to the right. Oops, sorry, wrong spot. Up 1, over 1 to the right, up 1, over 1 to the right, and you could keep doing that. When I go to draw the line, though, I said there has to be a hole at negative 2. You could also notice that you go down 1 and over 1 to the right, down 1 and over 1 to the right. But when I'm at negative 2, I said there should be a hole here, so that should be an open circle. And you could draw your line through this. Don't draw your line through the hole, but down 1 over 1. After that, the line continues. It's the same line, except for there's a hole at negative 2. Now, if you're not sure how to find the value of the hole, right? In other words, where's the y value that goes along with the x value? All you do is substitute it in, right? So the hole at x equals negative 2, you sub in to get the y value. You have y equals x minus 2, so the y value would be y equals subbing in negative 2 minus 2 equals negative 4. So we have a hole at the coordinates negative 2 comma negative 4, which happens to be where I graphed it, right? You could graph that first if you wanted to. Negative 2, down 1, 2, 3, negative 4 be there, and you have a hole. So this function is still the equation of f of x equals x squared minus 4 over x plus 2. But it looks like the line y equals x minus 2, except for it has a hole at the spot where you cancel those factors out. So that part in your domain that's excluded. So it has a hole at negative 2. So hopefully this was a good refresher for polynomials and rational functions. You'll see a lot of this if you're working throughout calculus where you might have factors that cancel.